And now, I'd like to introduce our presenter. Jeffrey Hesler is the CTO of Virginia Diodes and a visiting faculty at the University of Virginia. For more than 25 years, he has worked to create new technologies that utilize the terahertz frequency band for scientific, defense, and industrial applications. He has published over 200 technical papers, is a member of IEEE Technical Committee MTT-21 Terahertz Technology and Applications, and is a co-editor of the IEEE Transactions on Terahertz Science and Technology. Terahertz systems based on his innovative designs are now used in hundreds of research laboratories throughout the world. So, without further ado, let's turn our attention to wideband millimeter wave measurements from 50 gigahertz to 1.5 terahertz with Jeffrey Hesler. Hi.
All right, so I'll go ahead and get started with the talk here. So I'm going to talk today about some work we've done at Virginia Diodes on, particularly focused on wideband millimeter wave measurements from 50 gigahertz up to 1.5 terahertz. The outline shown here, I'll start with a kind of brief talk about some of the applications that have started our work in terahertz field and how those have led into commercial applications, and then just who we are and what technology we use, and then focus on test and measurement equipment for up at these terahertz frequencies, looking at just general generation and detection of signals, and then focusing on the generation testing, particularly of wideband modulated signals. Yeah. So certainly the start of our company, we came out of the University of Virginia. There's a lot of terahertz work done in our town of Charlottesville, Virginia. We have, and so we've worked for a long time on various scientific applications over kind of a wide range of fields, from radio astronomy, molecular spectroscopy, fusion plasma research, has diagnostic tools throughout the terahertz range, from essentially microwaves all the way up through 3 terahertz and pretty much at every wavelength. And so one of the things we were involved with early on is the Atacama Large Millimeter Wave Array. It's a radio telescope array on a high plateau, 5,000 meter plateau in Chile, with operating from around 100 gigahertz up to 1,000 gigahertz. And amongst many other things this has been used for, that black hole image that was put out recently, that was done partly with this Atacama Large Millimeter Wave Array, which uses our terahertz technology as one of the components in the receivers for that. So that's kind of the heritage, and but what we've been seeing over the past, particularly kind of 5 years, but even a bit longer, and accelerating recently, our commercial applications are really starting to pop up at up above 100 gigahertz, still relatively low frequencies, but moving higher and higher, as we'll see throughout this talk. So things like concealed weapons detection. This is an image from, actually I pulled off the UK government's website for the City of London, looking at testing of a terahertz imager for use in the London subway to detect large knives, which is a problem they've been having in London, is the knife attacks, apparently. And so they're looking, and I think they're now starting to deploy these sort of systems actively in the subways to deter these type of attacks. But a lot of other commercial applications, weather forecasting and cube satellites, have been really picking up a lot of steam. There's a lot of interest in using kind of hundreds of gigahertz radiometers for improving weather forecasting, collision avoidance radar, a lot of interest to the community today. The chemical biological hazards, medical diagnostics, and then the real topic today, wideband and secure communications, which has really taken off the last few years. And so focusing again on communications above 100 gigahertz, so-called 6G, I just, as one example amongst many, many other companies and even countries touting that they're really going to focus now on 6G starting already. Ericsson put out this technology review back in 2017, talking about microwave backhaul beyond 100 gigahertz. And last fall, Ericsson, together with Deutsche Telekom, demonstrated 100 gigabit per second link demo actually in Athens. It's an 8x8 line of sight MIMO. It was at E-band, so still sub 100 gigahertz, but still showing the really interest these the big players in communications are showing in even in 6G, not to say nothing of 5G, which is starting to be rolled out. So from that technology review, some of the use cases, just to kind of set a little background, these are some of the particular applications. And if you look at these kind of macro or small cell backhaul, and then kind of a whole bunch of other applications from kind of stadium events to airport connectivity and wide range where people are now seeing that this kind of so-called 6G will be of interest to and really provide a benefit and really technically needed. Frequency allocation, there are kind of oxygen and water lines. So this is going from 0 to 450 gigahertz, where you can see there's the 183 gigahertz water line. D-band, which is, again, people have been talking about a lot recently. This kind of 110 to 170 gigahertz, there's been a lot of interest in that. But even higher, there's all this spectrum, lots of spectral bandwidth available, even taking into account these water lines. So maybe not for long distance, but for kind of last mile or short range, there's a lot of interest just because there's so much bandwidth available. To give kind of some examples, these are some recent policy regulatory activity from last year and early this year. The FCC in the U.S. starting to look at bands all the way up to up to 245 gigahertz, to a 2 gigahertz chunk. The UK looking at things up to 200 gigahertz here, and then looking at the World Radio Communications Conference that was held last year in November. Before that conference, there weren't any allocations above 275, but they actually made allocations all the way up to 450 gigahertz, with a lot of interest to study some of these higher bands and kind of how to share these bands. And so, yeah, fixed and mobile allocations all the way up to 450 gigahertz. So just to kind of put all this in perspective, these are in the very, very early stages, obviously. We're still rolling out just 5G up to 40 gigahertz at the moment. And so talking about 450 gigahertz, we're talking very early stages, and they're not predicting rollouts till something like 2030. So this is still a long time in the future before these would be actual products in the field. Okay. So it's kind of the last thing I haven't really mentioned as far as applications. So you have all these potential commercial applications above 100 gigahertz that I've just kind of described. But developing these, the other thing you need is just test and measurement equipment. And that test and measurement equipment needs to be better than the devices and instruments that are being developed, both in terms of kind of power, bandwidth, the distortion, intermodulation, things like that. And so so that's what I'd like to focus on here, is kind of largely test and measurement equipment in these kind of millimeter wave to terahertz frequencies. As far as these test and measurements, there's kind of a wide variety of devices that need to be tested, from packaged devices in either waveguide or coax, on wafer. You've got differential devices, over-the-air testing. Also, there's a lot of different tests that need to be performed, from noise figure, distortion, EVM, S parameters, antenna patterns, and so So there's kind of a lot of different aspects of testing that need to be covered. And so you've got at microwaves a lot of test equipment, signal generators, scopes, network analyzer, spectrum analyzer, and a lot of additional equipment. And so then the question is, how do you extend this up into the mmWave and terahertz frequencies, and kind of to what quality can these be extended up? And so I'll give some examples of that throughout the talk today. Okay, so a brief introduction to Virginia Diodes. We're again, came out of the University of Virginia. Our original focus we're about 20 years old now. Original focus was on really basic science, applications, astronomy, but this kind of emergence of applications, we've been doing a lot of work on terahertz test and measurement. So what is our core technology? Really, our core technology is taking nonlinear diodes, a very simple device, the Schottky diode, just a metal semiconductor junction, using that nonlinearity to extend traditional microwave technology up into the millimeter waves and terahertz. And so that strong base of oscillators and amplifiers and test and measurement equipment available down below 40 are now down below, say, 100 gigahertz, the frequency limit for kind of the readily available technology is kind of moving up steadily, kind of week after week, year after year. And so trying to take that technology and extend it up using the Schottky diodes efficiently up to terahertz frequencies. We have our own very small captive clean room at Virginia Diodes, so we do fabricate these devices ourselves. We make flip chip diodes, so I've shown a few examples off to the right here. We need to have very low parasitics, capacitances, and inductances in order to operate up these high frequencies. We have flip chips as small as 50 by 100 microns, which is much, much smaller than typically the smallest, like an 0402 or even an 0201. It's kind of surface mount type technology. These are much smaller chips, but we were able to handle these and even solder them into housing. So a lot of challenges just in assembly and manufacturing. For the higher frequencies, we tend to integrate the diode with the coupling circuitry. So here's a few cases of diodes with microstrip lines you can see kind of running off. And with these, we're able to operate up to 3 terahertz or even higher for these different frequency bands. Okay. So with that as a brief introduction, I'd like to kind of switch over to kind of how we generate power and detect power at terahertz using these Schottky diodes, and kind of give some examples, some performance examples. Okay, so for signal generation, and we'll see a different example of signal generation later, but I'll kind of come back to this. But basically just using the nonlinear, the Schottky diode, either a variable capacitance or a variable resistance, send an input signal down at some low frequency, and then look at harmonics coming out of that device. The harmonics factors we look at are usually just going to be either a factor of 2 or 3, a doubler or a tripler, so relatively low harmonic factors, just to keep spectral purity and use balance type designs. So if you look at kind of power from solid state sources kind of across the frequency range, the kind of low frequencies below 100 gigahertz, the green curves are amplifiers. High frequencies, these are cryogenically cooled quantum cascade lasers coming in from the optical end. Fundamental oscillators in kind of orange here with relatively low power but going to very high frequencies. And then the blue are these basically Schottky diode multipliers. These are results from a variety of groups around the world, but just showing that once you get to these kind of few hundred gigahertz range, these Schottky multipliers are very important source of generating power up at these high frequencies. Okay. So the way we do this, we use waveguide-based components. We take, you can see the Schottky diode in the lower left. We kind of mount that in a split block metal type housing. We use waveguide pretty much because of the low loss. So as one example, at 600 gigahertz, a microstrip line is going to have something like a dB per millimeter loss, whereas waveguide is going to be less than a tenth of that at 0.08 dB per millimeter. So we try to get use waveguide as much as possible, but we do obviously use microstrip lines and coplanar waveguides and other things to couple to the diodes. And we have these type of multipliers to up to 3 terahertz. And so then an example of one of these waveguide housings shown at the bottom, a frequency doubler. Before we move on to kind of look at these in a little more detail, I'd like to look at the waveguide interfaces and then power measurements, just something I wanted to bring up just real briefly. We use an IEEE standard waveguide interface. This standard was released in 2016, and I've got some of the details and the title of that standard here. And this kind of helps to allow to make sure components from different companies are compatible and will work. We'll be able to interconnect together. And so I've shown an example one of these. It's very much kind of like the standard classical waveguide interface with a little bit of a few changes here and there to help improve performance up at the high frequencies. And we're actually actively using these now up to 1.5 terahertz, and there's some details on our website, and then also you can find that in the IEEE documents for this P1785 standard that came out. Power measurements, we rely on our own power sensor. It's kind of become the de facto standard back from the ALMA days for greater than 100 gigahertz measurements. It's a dry calorimeter and WR10 input, and we have tapers to taper to higher frequency, but we routinely use it up to 3 terahertz and even higher. It can measure quite low power, even sub-microwatts as power is possible with some careful kind of signal processing, and traceable to 110 gigahertz, and we're now working to extend that above 110 gigahertz. There's clearly a need for that with all these applications greater than 110 gigahertz coming up. So back to the Terahertz generation. So these we use these multipliers in what we call amplified multiplier chains, which is you take some low frequency synthesizer, you integrate it with some usually like mimic pre-doublers or triplers, amplifier, and this is I think a photograph of a gallium nitride amplifier at around 40 gigahertz, and then use those to drive these terahertz multipliers. We use kind of balance type designs to reduce, and we also do quite a bit of filtering to reduce the number of harmonics that come out of these. So even though we might drive it down at say 10 or 20 gigahertz, the majority of the power will come out at this desired n times the drive tone. There will be some power at integer multiples of that drive tone, unwanted harmonics, but those are usually down 20, even 30 or 40 dB down from this main tone for most of our sources, and that's something we'll see a curve of that later. So using that, you can then take some standard just 20 gigahertz signal generator, plug it in to the back, and sweep across and get power. In this case, this is a WR3.4 system covering 220 to 330 gigahertz with around 6 to 7 dBm of output power across the entire band. So you just pretty much sweep the synthesizer and you'll get a sweep across this with no tuning or anything like that. So instantaneous sweeping bandwidth over 40%. Okay, so now to switch over to signal detection. Basically the same type of approach. We're using a Schottky diodes, but in this case, instead of a multiplication type of prep, we're just using a classical heterodyne, just using the nonlinear of the diode to give you the difference between two frequencies, just classic heterodyne. And then that's a waveguide housing with one of these mixers on the right. So if you look inside these, it's very similar to what I showed before for the doubler. It's a waveguide type structure, split block. The diode is, so you can see here, one of the diodes on the right. That's mounted inside a metal housing that is then put together. The diodes are kind of in the center of the split. In this case, we're actually using 2 diodes to get a balance type anti-parallel balance configuration, which lets you operate at an LO about half your RF, so it's a second harmonic mixer. But even so, we can get noise figure pretty much as good as you can get with even a fundamental mixer. So this is an example at D band, where we're getting around 8 dB noise figure, single sideband across most of D band, rolling up a bit at the edges. Actually, this is even going outside the standard waveguide band. And so, oops, looks like I can't. Looks like I've lost the ability to change the slides. Oh, there we go. All right, there it is. Sorry. Okay. All right. So but I still wanted to make the kind of point that this is not a classical high harmonic mixer, and so I just wanted to kind of briefly talk about that. So a lot of the traditional spectrum analyzer extenders have been these high harmonic mixers, where essentially the LO is sent directly to the mixer diodes without any multiplication. In some of the more modern harmonic mixers, there is often some pre-multiplication to basically reduce, but still the harmonic numbers are something like 4 or 5, something along those lines, and then maybe some pre-multipliers. But what this means is you get this kind of mixing with all these harmonics. This leads to a very simple and low-cost device, just pretty much feed your signal into your nonlinear Schottky diodes, and you now have a mixer. Disadvantages, you tend to have quite poor conversion loss and therefore relatively low sensitivity. And you are also mixing, there's no preferential mixing with these type of devices. You mix from each of the integer harmonics that tend to fall within your band. And so that kind of adds some complexity to understanding what is coming out of this when you use this in a spectrum analyzer. There are things like signal ID you can use, but there are a lot more signals than you would normally have. So what we're doing instead is we're using a second harmonic mixer, as I mentioned. So in this case, you would send in a low frequency 10 to 20 gigahertz source, send it through one of these amplified multiplier chains to generate a millimeter wave local oscillator, and then that would then get mixed with the RF. And so in this case, you've now got predominantly just mixing off this desired LO tone. The upper and lower sidebands both convert down these, but you have very little mixing from these other harmonics. In this case, down 20, 30, 40 dB. So they're still there, but much reduced. And so this allows you to have much better sensitivity. And so I wanted to kind of talk briefly about sensitivity of these devices, spectrum analyzer detection limit, kind of how they affect what signals you can measure. For small signal detection, thermal, just Johnson noise, KTB, is still a key limitation. There are other things, antenna losses, and some of your mixer noise temperature and things like that. Traditional mixer figures of merit that we use, mixer noise temperature, that was used in the astronomy community. I think most people are probably more used to using mixer noise figure, which is just related this kind of 1 plus T mix over T naught, where T naught's the ambient. And so these are related parameters. For a spectrum analyzer, the kind of corresponding figure of merit for a spectrum analyzer extender is this displayed average noise level, which is just, if you're looking at the noise on your spectrum analyzer, what is the noise for in dBm per hertz, essentially. So it's kind of a noise spectral density that would be displayed on your screen. So that really sets your minimum detectable signal in a 1 hertz bandwidth. Is another way to look at that. And one thing to note is all these figures of merit are input referred, and so the output thermal noise of the mixer is kind of referred back to the input using the conversion loss. And so as a general rule, if you have high loss in your device, you're going to typically have worse sensitivity. It's a little more complicated than that, obviously, but that's a reasonable rule of thumb. So if we look at one of our WR140 to 220 gigahertz spectrum analyzer extender and look at what would we expect for this displayed average noise level. So we've got a mixer, some sort of an IF amplifier. If we kind of add all this up, we end up with a system mixer noise temperature around 2,000 Kelvin. And so then when we look at the input noise, refer that to the input, we end up with something like minus 165 dBm per hertz for that 200 gigahertz spectrum analyzer extender. And so if we go in and measure one of these, this is a measurement of across a WR5 band, and we're measuring something like minus 151 dBm per hertz, not this 165. And so what's happening here? Why don't we get that minus 165? Well, if we go look, it ends up, this is really just a limitation of the spectrum analyzer. The spectrum analyzer has a maximum input that we can feed into it from our IF signal. And so we actually have to pretty much have no IF gain following the mixer. And so the spectrum analyzer ends up setting our noise forward, so that limits us to this minus 150 dBm. If we just simply add this gain back in, and we've done this, we have a high sensitivity option where you have to kind of be careful. If you put in your full peak power, you can actually compress the spectrum analyzer, or it'll send out warning errors and stuff. But using this, we've been able to get below minus 160 dBm per hertz for certain applications where people really want to look at very small signal levels, and we can do this up to quite high frequencies. So we understand why we're only getting the minus 150, and just simply adding an IF amplifier, you can really boost that up to minus 160 or a bit better. Okay. So then so if we look at the DANL for the VDI spectrum analyzer extenders, we've got pretty much minus 150 dBm all the way up to 750 gigahertz, and then around minus 135 up to 1.1 terahertz, and we're actually working on a new version where we should get that closer to minus 150 as well. Just for comparison, and to show kind of the strength of these as compared with the harmonic mixers, I tried to estimate this displayed average noise level. It's a little hard to find that exact specification, but I did my best to interpret it, and it's looking, you see things typically something like minus 110 to minus 130 gigahertz at 100 gigahertz, dropping pretty rapidly as you go up to the higher frequencies. And so at 500 gigahertz, you're down to only about minus 100 dBm per hertz for even a modern, quite high performance harmonic mixer, which has these pre-multipliers. So, and the range here is to represent different manufacturers. Okay. So then spectrum analyzer extenders, basically, in this case, you're just taking the kind of spectrum analyzer extender cable, the external mixer cable coming out into this housing, and you can just extend the capabilities of your spectrum analyzer. So this is an example of the intrinsic conversion loss of the 500 to 750 gigahertz with about 15 dB conversion loss, which is why we're able to get the high sensitivity for this device. This is a measurement of a spectrum of a 625 gigahertz source. You can see the harmonic content kind of in here, but it's down at the kind of minus 25 dBc level, so we're quite happy with that. That's kind of our relatively usual performance with the main power in this main tone. You can then go ahead and do phase noise measurements. This is a 700 gigahertz phase noise measurement where we're able to measure all the way down to a 10 hertz, all the way up to 10 megahertz, and the phase noise follows what you would expect theoretically at a 20 log n rise of the phase noise upon multiplication, and so it kind of matches the theoretical phase noise quite well. Okay. We've also done some work making compact spectrum analyzer extenders, both kind of a mini version and then this kind of micro MixAM C-I. These have the same sensitivity, but reduced weight, reduced size. And so these are the people doing antenna measurements and things like that are interested in reducing the size of what they need to put onto their robotic arms for doing measurements. And so we have these kind of coming out now as well. And so one example is this is the NSI-MI spherical near-field scanner. This is one of our modules mounted on the back with a standard gain horn coming out the front, and then you can see the device under test here. And so the smaller this device is, the less constraints it puts on what type of an arm, what weight that needs to hold, and the faster it can move. So it really improves that. And so then these are used in one application, automotive emissions testing. Take just a bunch of these, and then you can look at it, do emissions testing. Because of this low DANL, you can accurately and relatively easily and fast measure these emissions up to the high frequencies. Okay, so go to the final topic, which is focused on wideband modulated signals, both the generation and detection of these. So I've mentioned and I showed this graph in the bottom right before. This is kind of the traditional spectrum analyzer extension mode. And for our devices, you essentially have the spectrum analyzer. You have the external mixer port, which goes out and feeds the terahertz extender. And when you look on the screen of your spectrum analyzer, you see the actual frequency, 500 to 750 gigahertz in this case. In order to deal with the spectral confusion, the upper and lower sideband issue, there's signal identification of one form or another. There's different algorithms you can use, but typically it's the basic is to do two sweeps, one assuming upper sideband, one assuming lower sideband, and then kind of comparing those two, and things that don't move will be counted as a true signal. But this is so for a single coherent tone, this works very well. But if you have either a drifting signal or a banded communication signal, this type of signal ID doesn't work so well. And so trying to do analysis using this type of approach, it can be quite a challenge. And so so what we switched to in this case is what we call this a block down conversion mode. So in this case, you're not using the local oscillator synthesizer from the spectrum analyzer. You just use a standalone synthesizer, and you just feed the broadband IF signal coming out of this spectrum analyzer extender into the RF port. And so in this case, you take whatever chunk of terahertz bandwidth and just measure that with your spectrum analyzer. Here you can do instantaneous analysis. You can feed this into a spectrum analyzer, or we'll see examples later of feeding these type of signals into fast oscilloscopes. And so you can kind of analyze wideband real-time signals using this type of approach. And so this is kind of where we're mostly focused on for these broadband signals. So our standard spectrum analyzers do have wideband capability, but in order to get the best distortion, the lowest distortion and intermodulations, we developed these compact up and down converters, which are, you can see a schematic in the lower left. These are just basically a simplified version of the spectrum analyzer extender with as little in it as we could we tried to put in as little as we could so that it would be as clean of a signal as possible, least distortion. We have these up to about 200 gigahertz right now, and these are meant for really up converting and down converting broadband signals. And so these are the kind of systems that we're using for these, although our general spectrum analyzer extenders can do this with a little more distortion, but these modules are, because they're simplified, they're not as flexible as those, so you can't use them as such general purpose instruments, and so there are some trade-offs that you pay for getting this reduced distortion. So back to block down conversion, you have some signal up at, say, a few hundred gigahertz. You want to analyze this, and so you drive your spectrum analyzer extender with a synthesizer, and then just basically down convert this down into baseband. So just classic block. So the down conversion is relatively simple. we've got 10 gigahertz of bandwidth available at E-band, and that gets up at 300 gigahertz. It's pretty much 40 gigahertz of IF bandwidth, so you can get very wide IF demodulation for these systems. For the up conversion, here you just turn the process around. You just feed your broadband signal into your IF port of your spectrum analyzer extender or compact up converter, using, again, an external synthesizer, and you reproduce this signal up at the millimeter wave or terahertz, but what you run across is that you have, it's a double sideband mixer, and so you end up with an upper and a lower sideband. And so for some applications, that causes problems, and so you want to get rid of that lower sideband, and so try to chop that out. So we have been working on developing filters to allow you to upconvert and kind of get a good, clean copy of a signal, of some baseband signal up in the millimeter wave or terahertz range. So this is what that type of a system would look like. You've got your block up converter here in the center, signal generator for your LO drive, your arbitrary waveform generator or some other signal generator to feed in your wideband signal, and then follow that with a bandpass filter to knock out any leaked LO and the lower sideband or upper sideband, block either one, and then you can follow that to increase the power with an amplifier. And so this is kind of how we generate broadband signals. The reason we don't use our signal generator extenders to generate broadband signals is that they tend to distort the signal, both amplitude and phase. And so this way we can just generate a copy up at millimeter wave or terahertz without this distortion that comes up with the multiplication process, which is going to both expand the phase and distort the amplitude quite a strong amount. Okay. So for these bandpass filters, we've developed a whole series of these for different various communication bands. So these are a few examples down at E-band. So where this is a little hard to read, but it's 20 dB per division. So these are very steep skirted filters, quite low in-band insertion loss. I don't think, oh yeah, something like sub 1 dB in-band insertion loss, very low ripple, and then a very fast roll-off to allow you to kind of cleanly cut out the unwanted signals. We have these certainly show at the bottom one in D-band, although I don't have the data. And we've even, for various experimental applications, this is a 560 gigahertz bandpass filter that we did for a scientific application. And just to show that we can do these type of filters, here you can see it's more like about 2 dB in-band loss, still relatively low. But we can do these filters up to very high frequencies and get good precision and kind of hit the frequencies we want. Once it's been filtered and up converted, we then use waveguide amplifiers so that we can increase the power that's up converted by this kind of compact up converter. We have waveguide amplifiers available from about 50 gigahertz up to about 250 gigahertz. Gains are not very high for a single stage. It's only in the range of kind of 20 to 25 dB gain, but quite high output power. So more than 100 milliwatts down at up to about 100 gigahertz, and then even still something like 16, 17 dBm all the way up to 200, 250 gigahertz. And so with this, you can generate quite reasonable output power. And again, they're relatively flat, and so you can not distort the signal too dramatically with these amplifiers. So this is one example of kind of a compact up converter to generate a signal, and then a down converter here to, this is for a 140 gigahertz communication link demo that we did. And so in this case, we're sending in around an 11 gigahertz signal, multiplying it by 6, and then we mix this with an IF input from 4 to 8 gigahertz, which is our communication signal. We then filter that, amplify it, and then that goes out. In this case, it's going out into free space. And then we have a down converter, same local oscillator, and then that's down converted with an amplifier, and then you get a regenerated version of that exact same signal at the output. This was demonstrated for those that were at the Brooklyn 5G Summit last year. This was a demonstration they showed there, and it's being used by the group at NYU for doing channel sounding and other experiments. And then this is another example of a very similar system. I'll show a little more details on the measurements. This is a sub-terahertz test bed for 6G research. This was from a recent white paper put out by Keysight, and I've put the link for that down below. And so you can see kind of the VDI up converter and down converter kind of down at the bottom. And so what you have in this case is you've got an arbitrary waveform generator to generate the wideband IF. You've got a standard signal generator to generate the fixed LO for the up converter and down converter. And then a broadband, in this case a 33 gigahertz oscilloscope for doing the demodulation or detection of the signal. And then they're using their communication software to do the kind of analysis and generation of the signals and all that. And so using this setup, they were doing some measurements. This is for a 16 QAM signal at 144 gigahertz, using a simulated radio using these up and down converters. Channel bandwidth was around just above 4 gigahertz, and we measured an EVM of around 2%. And they had similar sort of quality measurements going up to 64 QAM type signals. And so here's a quite low distortion system with quite good output power at V band, and we're now developing even higher frequency versions of these. You can also push the bandwidth. This is now with 10 gigahertz of occupied bandwidth, with also you can see the 16 QAM signal in the upper left quadrant there, and the eye diagrams off to the right. And EVM just below 5%, so not quite as good, but this is quite a broadband signal here, and they actually pushed this up to 128 QAM for this signal, and we're able to get communication links and get things working. This was using some G-band converters. This is something we were very excited to see. This was the regulatory testing on the first 5G handset. This was done by PC Tests, and so all these documents were released, but it's using this basic type of hardware to do all the regulatory testing for these. And so these are starting to a lot of interest in 300 gigahertz and now even up to 700 gigahertz for emissions testing for a variety of devices, as people are now pushing to D-band, and you've now got the requirement to test these harmonics of these up to quite high frequency. And so it's been quite a change again over these past few years for these type of systems. Okay, so I'll go ahead and stop there and summarize. So the THz technology, it's an emerging field with lots of basic scientific applications, although there now are a lot of commercial applications that are really starting to come along and accelerate, particularly with this wideband communications and also the automotive radar. Our big focus is in test and measurement to make sure you can get good, accurate testing of these devices so that you can develop new devices. Some of the takeaways, you can certainly use existing equipment and extend it up to these terahertz frequencies. You want to use these true mixers rather than the harmonic mixers to get the very high sensitivity DANL, which both allows you to measure small signals, but also allows you to speed up your measurements, because you can potentially use wider IF bandwidths and still detect the small signals. So there's a lot of benefits to this sensitivity. You want to put your test probe near the device under test. Cable loss is a big challenge, and so particularly at the lower frequencies, you don't want to run 1 millimeter coax out to some device, because you'll lose all your sensitivity on that cable. And then, so high dynamic range obviously matters as well. So just a few takeaways, and I'll go ahead and stop there, and I hope, think I can answer potentially a few questions, and we'll go from there.
All right,
right, Jeffrey, that sounds like a plan. We did have a couple of questions come in.
Oh, great.
So the first question says, how wide a band can be covered instantaneously by the Virginia Diode devices? Can pulsed ultra-wideband signals having a bandwidth of several gigahertz be measured correctly?
Great, yes, okay. So certainly we've done a lot of work on various pulsed applications, and we've pushed things to kind of, I think, we've done some measurements of very fast pulse systems where the pulses were of order kind of tens of picoseconds, and we've been able to, we were actually able to resolve that down to about 30 picoseconds, but that was actually the limitation of the high-frequency oscilloscope, which was, I think, about a 30 gigahertz scope. And so a few gigahertz bandwidth is something that's very doable with these type of systems. It's something we pretty routinely do. And again, as the example I gave showed, we're doing even this 10 gigahertz wide communication link, we're able to do 128 QAM type signals. And again, for 150 gigahertz signal, it's about a 20 gigahertz IF bandwidth that can be instantaneously analyzed. So, yes.
Okay. The next question is, what is your recommended calibration interval for a typical spectrum analyzer extender? Is it possible to get a 17025 accredited calibration for these SAX right now?
That's a very good question. It's something we're actively working on. So at the moment, we do routinely get the systems back to check them in our laboratory, but we're not accredited in kind of to that level. And so we are kind of actively pushing to at least get that sort of a calibration up to 110 gigahertz. And as I mentioned, one of the key challenges to pushing beyond 110 gigahertz is having traceable power measurements. And that's something that groups kind of around the world are actively working on to push that to at least 170 gigahertz. We cover D-band. And also, we're involved in several projects trying to push that up to 300 gigahertz or even higher. So it's something that we're actively working on. We do routinely get the systems back and verify basic performance, verify DANL. We can do that, but we're working on that full certification that you mentioned. So.
All right, sounds good. So at the moment, I don't see any other questions, but I would like to encourage everyone that's on the webinar, go ahead and chat the questions into us so we can have Mr. Jeffrey answer them. Let's see, I guess I'll wait a second here and mention that we have another upcoming webinar, and we'll be covering preparing certification applications for radio approvals. That's going to be on May the 21st at 1 o'clock Eastern Time. So if anyone's interested in looking out for that, you can go to our website and register for the webinar if you're interested. Looking here for any more questions. And Jeffrey, I think we've answered all the questions.
All right, sounds good to me. Great. I'm happy to answer any questions via email. So I think you have that questions email on your slides, I guess, and I'm happy to answer any other questions. So.
Okay, great. Well, I guess that's going to do it for now. If we don't have any other questions, thank you so very much, Jeffrey Hesler, for taking time out to enlighten us about wideband millimeter wave measurements. On behalf of Washington Labs Academy, I want to thank everybody for their attendance, and I'll go ahead and end the event. I want everyone to enjoy the rest of their day and be safe. Bye-bye.